Okay, so we are wrapping up our first week with an introduction to functions, and to do this, we are going to revisit linear equations. Now they're going to be linear functions, okay? You're going to find that a lot of what I'm going to talk about in this video is review from when we did linear equations and linear graphs earlier in the year. So that first part of the material, I'm going to move through pretty quickly. And then I'm just going to suggest if you have things on that that you're not sure about, maybe go back and review the older material from where we did this the first time a few weeks ago. But the second half of this video, I'm going to start talking about a specific type of way that we interact with linear functions as far as being able to interpret the meaning of the function. And this is an important skill to have as we take mathematics and we apply it to the real world. So this is where things start to get more realistic. Which for some people that's important to them, right? They look at the stuff that they do in math class and they're kind of like, well, when would I ever use this? Or this is the type of thinking that makes that gap or bridges that gap, so that it's not just something you do in the classroom once when you're in high school and never again. The type of thinking we're going to look at today provides a bridge so that now we have the ability to use these mathematical tools that we've learned in high school math class in the real world and in our real life. As a side note, because some of you will find this also to be important, the types of thinking that we're going to look at in the second half of this video are often tested on the SAT. So if you're someone who's preparing for the SAT and you're hoping to do well, then we're going to look at some questions that they like to ask on the SAT. So with all of that said, let's get started by looking at the learning objectives for this video. 3 learning objectives for today. The first one you can see is simply to make a table of values. The second one is to make a graph. You're going to see when we go through those 2 things that it's exactly the same process as it was when we did this with equations. The only difference is that we're going to use function notation instead of just a plain old y. That's the only difference, okay? And then the last thing, as I was saying, is this is the bridge that connects us to real life applications for functions. And specifically for linear functions, linear equations. That's specifically what we're looking at right now, are things that are linear. So maybe the first reminder that I'd like to provide for you is, what does it mean to be linear? Okay, so remember, linear, where that name comes from is because the graph looks like a line, and that's usually what students jump right on first, is that linear means the graph is a line, and that's 100% true. But when we're looking at a linear equation, remember the key that we're looking for, the feature of the equation that guarantees it's going to be linear, is that we have a plain old x that doesn't have any exponents. It doesn't have any radicals or square roots or anything like that. It's not in a fraction, specifically not in the denominator of a fraction. It's just a plain old regular x, okay? So those are the types of things that we're going to look at, but as we discussed in the previous video, we're not going to use y's, generally speaking. We're going to use some name for the function, but everything else is the same. So the first thing that I want to make sure that you're comfortable with is the idea that we have learned before. M is a slope, and we've talked about that can also be referred to as some sort of pattern in the problem. It can also be referred to as a rate of change. Okay, there's lots of ways that you can use the words or talk about the things called slope. Mathematically, as far as a formula goes, we talk about that the slope is the rise over the run. These are all things that we've discussed before. And so that's what I meant at the beginning of the video when I said if there's pieces of this that you don't remember from before, the best thing to do is to go back and look at those old videos, because I'm not going to go into much more detail than that right now. Okay? Then the second piece of the equation that we've learned about before is the b at the end, and that we typically call the y-intercept. But we also talked about that that's the initial value for the function. We talked about its step number 0 on the function. We gave that one different names also. We had an ability to calculate its value with a formula. We said that it would be equal to some y value minus the slope times some x value, okay? For slope, we had a formula also that was subtract two y numbers and divide that by the difference of two x numbers. Okay, so these are all things that we've talked about before. And potentially you might need all that information again. All right, so that's just a quick review of the things that we've already discussed with these. So let's jump into two fast examples that connect the idea of function notation to the types of things we've done before. Okay, so for example, one of the things that we've done before is we've made a table and we've plotted a graph or drawn a graph. Okay, and so we're going to do both of those things with this function right now. If you feel confident that you remember how to do this from before and you can extrapolate out what we learned with y's and x's and make it work with f of x's and x's, maybe pause the video right now and give this a try on your own. Okay, hopefully you've given this a try, but if not, that's fine. Normally what we do is we make a table where we have an x and we have a y. But remember what we've said is that this is the same as having a y. So typically in our table when we're working with functions, we would write f of x, or sometimes you'll see people write y equals f of x, just so their table reminds them that those are the same things. It doesn't really matter how you label your table. Just recognize that the numbers that we put here represent both the f of x value, the value of the function, and they represent the y coordinate. Oops, got something on my finger there. Okay, so just keep that in mind. The rest of this is exactly the same. What I'm going to do is I'm going to pick some numbers for x. Because it's a linear function, it really doesn't matter very much what numbers we pick. So I'm going to do -2, 0, and +2. Okay, you could do different numbers. Maybe you did -1 and +1 or whatever. That's up to you, whatever. But those are the numbers that I'm going to pick for x. And then we're going to plug those into the equation. So I'm going to go ahead and make room here to do some work also, just to make sure that we're good with how we're going to calculate this. So here, if x equals -2, then what that means is I'm calculating f of -2. So I'm going to go up to my equation, and anywhere there's an x, I'm going to replace that with a -2 that's in parentheses. And then I'm going to simplify this using the order of operations. And so here I'm going to get a -6 plus 4. -6 plus 4 is -2. And so that's what I would end up there. Same idea with this one. I would do f of 0, which means I'm going to take my equation, and where the x is, I'm going to replace it with a 0 in parentheses. And then I'll simplify this using the order of operations. I'm going to get 4, it looks like. Okay, then I'll come down to this one. Those were the 3 that I said I was going to do. But if you did the other ones as well, that's fine. Okay, but that's basically what I would end up with. As a side note, if you did -1, I believe what you should have ended up with was a 1 for the value there. And if you did +1, I believe what you should have ended up with was a 7 for the value there. Okay, so those are the numbers that we're ending up with. Now we're going to come over here and we're going to make a graph. For the purposes of our discussion right here, I don't have graph paper handy. Actually, I do have graph paper handy. And as we talked about before, I would recommend that you do as many of these with graph paper as you can, because that makes your answer more accurate. It also, I take it back, I do not have graph paper handy. So I'm just going to do this by hand. But even if you're doing it by hand, really be careful to make sure that you're taking the time to try and make a nice, clean, and accurate graph. Okay? The more time you spend with this, the more careful you are with graphs, the better it's going to be. And especially when we start getting into more complicated problems, problems that have multiple functions in them, you're going to want nice, neat graphs for those. So the first point I have here is -2, -2. So I'm going to go back 2 for my x value, down 2 for my y value, and there I've got a point. If you made this as one of your values, there's -1, +1, so -1, +1. Okay, now I've got a 0, 4, so 0, and then 4 would be up here. And at that point, I'm kind of running out of room on my graph. I'd have to go up 7, which is up a little higher, whatever. So now I'm going to go ahead and just connect my dots. And you can see, because I didn't use graph paper, my graph is pretty close, but it's a little tiny bit off, okay? And we're looking for pretty decent graphs here. So try and get that as accurate as you can when you make that graph. Okay, so this is the first type of problem, and this is a type of problem that we did lots earlier in the class, and you did lots of that in your last algebra class too. So that takes care of learning objective number 1, be able to make a table of values, and learning objective number 2, be able to draw a graph. That brings us then to learning objective number 3, remembering how the different parts of the equation relate to real life. How they relate to real life. What do the different pieces mean? So again, as I said just a few minutes ago, in the equation, we have this thing that we call slope, and we have this thing that we call the y-intercept. But slope and y-intercept are terms that really apply mostly in the math class. You don't often hear people outside of math talking about slope and y-intercept, okay? Maybe skiers talk about slope, but nobody talks about y-intercept for sure. So when we start connecting this to real life, I like some of those other terms better. The slope is just a pattern. Anytime you have a problem or a situation or scenario in real life where there's this consistent pattern, something is changing in a regular pattern. You know, if you say somebody, on average, kindergartners are growing an inch per year or something like that. That's a consistent pattern. So when they're 4, they're going to be a certain height. When they're 5, they're going to be 1 inch taller. When they're 6, they're going to be 1 inch taller. And that's a consistent pattern. If you have a city and you say, okay, this particular city, on average, every year there's 100 more people who live in the city. Then in the year, 2015, there's so many people who live there, but 2016, there's 100 more people. And then 2017, there's another 100 more people, and so on. That's a consistent pattern. All of those scenarios are describing slope, okay? Think about when you go shopping for just a minute. If you go shopping and you go to the store and you want to buy your favorite whatchamacallit, and you want to get 5 of them, and whatchamacallits cost $2 a piece, then for the first one you're paying $2, for the next one you're paying 4, for the next one you're paying 6. That's a consistent pattern. That's a slope. That's what that is, okay? So all of these are scenarios where you're working with slope. Excuse me. Then we have this thing over here. We normally call it y-intercept. So this was the pattern. It's what's changing consistently in the problem, which is why we also call it the rate of change, okay? But then we've got the y-intercept. Then we have the y-intercept. The y-intercept is the value that the problem initially starts at, okay? So the other word that we called this was the initial, if I can remember how to spell initial, value. The initial value, okay? The initial value. There, I think that's spelled correctly, isn't it? I need to slow down and make sure that we've got things right. The initial value. That's something that doesn't change. There is a point in the problem where something is a fixed value, okay? So let's say, for example, I'm buying my favorite whatchamajiggets at the store. If they cost $2 a piece, initially, before I buy anything, I don't owe the store anything. When I first walk into the store, before I've picked any up, before I've gone to the cash register, I owe the store nothing. My initial value is 0. Now that's different than if I get a magazine subscription or something like that, where I have to pay a certain fee, or maybe a membership fee, right? Maybe I join a health club, and there's an initial membership fee for joining, a processing fee for the joining, just so they can fill out my paperwork and get me into the room. And then there's a monthly fee after that. So the monthly fee that comes after that, that's my pattern. But that initial value that I have to pay at the beginning, that's my y-intercept, okay? So these are the two things that you're going to be looking for in problems. And to help us with that, I have printed off 2 questions that came straight from an SAT test. And we're going to look at those 2 questions and try and break down, can we find what the pattern is, and can we find what the initial value is, okay? So maybe pause the video for a second just to read this, to become familiar with the question. Make sure you understand what the question is all about. Okay, so hopefully you've taken time to read this. So remember, when we work through a problem, we work through it in 5 steps. Anytime we've got a problem that we're trying to solve, we go through it in 5 steps. The first step is to understand. And for this particular problem, I cannot spell today, understand. Okay, for this particular problem, really we never have to go much past understanding. Maybe we go into a little bit of collecting data and organizing data. But we never get to the part where we have to actually like do math or anything like that. So the develop a plan and to carry the plan out and then to check your answer, those are things that on this particular problem, we never really have to do those, okay? They're just checking to make sure that we understand what the data in the problem is asking us. So that's where we're gonna focus on this. So Kathy is a repair technician for a telephone company. Well, that's nice for Kathy, but it doesn't really help me solve this problem. So we're gonna just ignore that. Each week, notice each week, right there, they're introducing a term that gives me a clue that we're gonna be talking about patterns. Every week, something is happening in Kathy's life. What happens? She receives a batch of phones that need repairs. Okay, so this is giving us an idea of things that are changing. Okay, there's these phones that need to be fixed. That's something that's changing. So that gives me an idea that I'm gonna have something to do with fixing phones as regard to my pattern. The number of phones she has left to fix at the end of each day can be estimated with this equation, where P is the number of phones left and B is the number of days that she has worked that week. I'm sorry, D is the number of days that she's worked that week. Okay, so in this equation, P is the number of phones that she needs to fix, and D is the number of days that she's worked. Okay, so this is a function that calculates how many phones based on knowing the number of days. That's what we have here. Okay, now the question they asked is, what is the meaning of the value 108? What is the meaning of the value 108? So if we think about where it's at, 108 is not being multiplied by the D. If we were to write this in our standard form, or our slope-intercept form probably is the better word, the function form, then we would have the negative 23D plus 108. The 108 is the constant at the end. So what did we say that constant was? That's our initial value. So the 108 has something to do with an initial value. So in the context of this problem, what would we mean when we're talking about initially? Well, it probably means how many phones she needs to fix on day 1. That's probably what it means. Every week she gets a number of phones. So let's just say she works Monday through Friday. That's what most people work. I know not everybody does, but let's just say she works Monday through Friday. So every week on Monday, she gets some phones. And then she works all week long fixing the phones. And the question that they're asking us is, what does the 108 mean? Well, I would say the 108, because it's the initial value, that must be how many broken phones she got at the beginning of the week. So let's see what we have here. Kathy will complete the repairs in 108 days. Nope, there's no part of the formula that predicts how long it's going to take. That's something we could calculate, but there's nothing that predicts that in the formula. Kathy starts each week with 108 phones. That's the one that I think it is. So I'm going to mark that as being, I think it's that one. Okay, we're going to come back to that. Kathy repairs the phones at a rate of 108 per hour. Well, remember that it said that this is the number of phones per day, how many days she worked. So because this says per hour, that can't be it. So it's definitely not A, it's definitely not C. Now D though, how many phones she fixes per day, the rate per day. Okay, so when I go back to the formula, the rate, the thing that is changing, that's the number that gets multiplied in front of the variable. So 23 must be how many phones she's fixing per day. So I think that this is my best answer. Okay, now recognize they could have just as easily asked what the number 23 meant. So in this problem, 23 means she's fixing 23 phones every day. Okay, so this is, or on average, right? Sometimes things happen, but on average, she's fixing 23 phones every day. So this is a type of problem where we are going to look at an equation, put it into the context of real life, and then interpret what those numbers mean. So let's take a look at one more. This is from the exact same SAT test, just a few questions later. This was question number 4 on the test. This is question number 6 on the test. So one thing that I want you to recognize is not only is this something that connects math to real life, but it is a more immediate concern if you are a junior in high school. As a more immediate concern, this is something that you will see on the SAT very likely more than once, okay? So here we go. Pediatrician uses the model. Remember, model is just another word for equation. And now we have learned that equation can also mean function in this particular context, right? When we're working with linear equations, linear things are always functions. Pediatrician uses the model to estimate the height. H is height. H is height, okay? So we're trying to calculate height of a boy in inches in terms of the boy's age. A. So A is age. How old the boy is to calculate how high they are. So if you think about this, that you go to the doctor's office when you're a little kid. Notice this says between the ages of 2 and 5. So we're talking about toddlers and preschoolers here. So the mama takes their toddler, or the daddy takes their toddler or their preschooler to the pediatrician. And specifically, this formula is for boys. This formula specifically is for boys. So they take their son to the pediatrician, and the pediatrician says, oh, your child is 3 years old, and there's this chart. And you might not know this because you're probably too young to have children that you take the pediatrician, and you're probably too old to remember when you were a child going to the pediatrician. But they have these charts, and they look at the chart and they look at how old the child is, and there's this chart that tells them approximately how tall they should be. Okay, so that's the idea that this is getting into. If we know how old they are, we can approximate approximately how tall they should be. And so that's what this formula is all about. Now, that's the real life. Let's get to the math. In this equation, based on this model, what is the estimated increase? Okay, so notice now we're talking about an increase. So we're talking about change. How much is something changing? We're talking about slope. That's what we're talking about. In the inches of the boy's height each year. Okay, so in this equation, if I want to find the change, I'm looking for the slope. Slope is always the thing that gets multiplied by the variable, right? There's my variable. So in this problem, my variable is A. The slope is the thing that's getting multiplied by the variable. So in this problem, we're multiplying the variable by 3. That's my slope. The value of B at the end, well, that's an interesting question. Maybe we'll visit that here in just a second. But the answer to this question is, it looks like on average, we are estimating that the typical 2 to 5 year old boy will grow 3 inches per year. So in inches, what will their height change per year? I think we're saying 3. Okay, now let's look at what B is for a second. In the context of this problem, thinking about what's happening in the story, in the context of this problem, what does the number 28.6 represent? What does the number 28.6 represent? So I'm changing the question. It's not going to be one of these options down here, okay? Now it's more like this question that we just did a second ago. What did the 108 represent? In this story, it represented how many phones Kathy got on Monday. But in this story, what does the number 28.6 represent? So think about that for a minute. All right, so I think what I would say is that 28.6, because that's the value of B, and B is an initial value, it has something to do with approximately how tall we expect the boy to be initially. So maybe that means in the context of this story, because the formula only works from 2 to 5, maybe that means how tall they are when they're 2 years old, okay? Or some formulas, this doesn't give us details. You have to modify things slightly, maybe that's how tall the baby was when it was born. Now that would be a really long baby. That's probably not the case in this situation, but it probably has something to do with the height or the length of the child at the beginning of this formula. And since the formula begins when the child is 2 years old, it probably has something to do with that, okay? Now, in the context of this story, like I said, we really don't have a good piece of information. It might connect back to when the child was first born, when they were 0 years old, okay? But the model doesn't work when they're 0 years old. So there's some sort of weirdness going on, which is probably why they didn't ask us for that question. But what they did ask us for is for this question, okay? So those are the types of problems that you're gonna see on tonight's homework. This, as you can tell, is also the type of problem that you might see when you take the SAT in a few months. But that is all we have for our first week where we've introduced functions, and for this last day of the first week where we've talked specifically about linear functions. Okay, thanks for watching. Have a good one.